So we're talking about the differences between a DFA and an NFA, between a deterministic finite automaton and a non-deterministic finite automaton, right? Now, in whoops. Well, it's working. It's got this correct. That should be N. So what's new about an NFA, a non-deterministic finite automaton, is that for a given pair, like the current state and the current symbol that's being read, there may be more than one next state, right? So in other words, more than one exit, or like output arrow to the next state. There can be more than one next state. Okay? So you could have, well, you could have 0, 1, or many exiting arrows, right, for each alphabet symbol for a given state that you're in. So you're generalizing a bit more. I mean, you could have 0, 1. That would be the case in a DFA, or many. Okay. Now another difference. So there's 2. So talked about like the first major difference. You can have multiple, or 0 exit arrows for a given state and input symbol. Okay, here's another one. Now in a DFA, deterministic, the labels on transition arrows, exiting arrows, they are members of your alphabet. Right? They are symbols of your alphabet. Okay? Yeah, symbols belonging to your alphabet. Okay? But in a non-deterministic finite automaton, an NFA, your exit arrows could be labelled with eta. Okay? Now, so that means with an NDA, your arrows, your transition arrows, they can be labelled either with symbols of the alphabet, alphabet symbols, or with eta. Right? So you have more options with an NDA. Okay, and you can have, for a given state, you can have 0, 1, or many exit arrows with this label, eta. And you may say, so what? Why are we defining NFAs this way? What's the point? Yeah, it's a perfectly reasonable question. You need to wait a while. You'll see, obviously, that it does serve a very useful function. You'll see how powerful this concept of non-determinism is. It's it was a great invention when it was made. Okay, all right. Now this is in a sense thrown at you at the moment. It's sort of just setting up the differences, defining what an NFA looks like, what its state diagram looks like, sort of, the features it can have, the differences it can have from DFAs. Okay, but all right. So okay, we've done that. So how does an NDA compute? Like, how does it work? Right. So essentially, it just chuffs along in the same old way as an NFA. Making a lot of thinkers lately. Right. So how does an NFA, non-deterministic finite automaton, how does it compute? Well, it just proceeds in the same kind of way as a DFA until it comes to a state where there are more than one possible exit arrows for the same pair, like the given current state and a given input symbol. So when there's more than one possibility, then something weird happens. For an NFA. Okay. Now what happens is, like for example, in the previous session, we were in state Q1, and the input symbol was 1, and there were two possible next states. It went back to Q1, or it went to Q2. Okay. Now when that happens, an NFA, it performs some magic, and it makes a copy of itself, and one copy of the machine just proceeds along one of the next states, and the other copy, its next state would be the second possible next state. Like for example, for Q1. Well, you can't see it, but so imagine you're an NFA, a non-deterministic finite automaton. Your current state is Q1, and you look at this state diagram, state transition diagram, and you see that when the input is 1, you have two options. You can transition back to Q1, or you can transition to Q2. At that stage, because you're an NFA, you now make a copy of yourself, abracadabra. So now there's like two of you, and one takes as next state Q1, and the other copy takes as next state Q2. And then you now have two machines, and they just continue on in parallel, right? So in a sense, you can say that non-deterministic computation is you can look on it as a kind of parallel computing, right? Because in a sense your machine forked, it's split into two, and sort of magically made a copy of itself. And one copy went down one branch of one path, if you like, if you think of the state diagram as a graph. And the other copy of the machine went down the other path. Okay, and the two just operate independently, and so you now have like two machines doing their thing, following the different branches of the state diagram, the state transition diagram. Okay, so that's sort of a major feature difference of an NFA compared to a DFA. Okay, so so the copies then they just work in parallel, right? And if this sort of thing happens again, so imagine one of those copies comes to a state and there are two or more possibilities. Well, it splits again, so you could get splitting and splitting and splitting. You have a whole tree like of splits, right? Sort of an upside down tree. So an NFA can do that. Okay, now there's another possibility. Say, and we mentioned it a bit previous session, I think. Imagine you're at a node, like in your state diagram. You're at a node corresponding to your current state, and you have a look at the input symbol, and there is no arrow, exiting arrow from your node, from your state, that corresponds to, with a label that has, whose label, there's no arrow with a label that is equal to the input symbol. Right? There's no corresponding exit arrow. What do you do then? You die, right? And that branch is then terminated. It's like somebody gets a root and snips off that root. So that branch of computation then dies. Okay? So if there's no corresponding exiting arrow with a symbol that's equal to the symbol being red, then that branch dies. Okay? Right? So, right. Now, how does an NFA itself accept a string? Now, you've got all these splittings, all these forkings going on. Okay? And every time there's more than one exiting arrow, you get magically a copy is made. Okay, so how does this magically copying device, this NFA, how does it terminate? How does it function? How does it compute? How does it accept a string? Well, the answer is if one of those branches accepts, just one of them, if one of those branches accepts, the whole tree accepts. In other words, the whole NFA says accept. Okay? That's the essential idea. So imagine an NFA then as a sort of branching, multi-rooted sort of structure. Okay, each branch, and if one of them accepts, the whole thing accepts. And that's how an NFA computes. Okay? Alright, so just a minute or two done here, because my wife has just walked in the front door here and is waiting patiently for me to finish, so I'm indirectly telling her I'll finish in about a minute. Okay? Yeah. Right. So look on, I was saying a bit before, look on non-determinism as kind of parallel processing, like a parallel computation. Okay? So what I've been calling branches, you could call that a process or a thread. Parallel computing people tend to use the word thread. Okay? And these threads or branches or processes, they're all processing away in parallel, at the same time, independently. Okay? Until one of them, hopefully, one of them accepts. And the moment that happens, once that happens, the whole NFA accepts. Right? Yeah, that's what I'm saying here. So if just one branch, or thread, or whatever you want to call it, accepts the NDA, the non-deterministic, and I've done it again, NFA, right? Non-deterministic finite automaton accepts. And that's sort of the essence of the power of non-deterministic computation, because you get all this forking, there's all this branching, and they're all independently doing their own thing, and hopefully one of them will accept, and then the whole thing accepts. Okay? And I'll follow on with that idea on the next board. Ciao.